and welcome back to another lecture of Statistics 479 Time Series Analysis. In today's lecture, we're going to continue to look at seasonal ARIMA models, but we're going to do it in RStudio, and that is always a good time. So in today's lecture, we're going to spend the entire time looking at the prescription drug data set that we had looked at earlier in this course. But now we're going to use all the tools we have about fitting ARMA processes, fitting ARIMA processes, and fitting seasonal models to our data, as well as looking at linear models and lots of different ways to model time series. So, as I've said more than once, time series is really an exploratory subject. We have to spend a lot of time fitting models and trying to figure out what works best for our data set, and that's what we're going to do in today's lecture. So, come join me, and we're going to look at some RStudio code. And welcome back to another lecture of Statistics 479 Time Series Analysis. Today, we're going to look at the seasonal ARIMA model again, but we're going to look at it in RStudio with some real data. This will probably be a more useful lecture, or one of the more useful lectures, because we're actually going to look at how to analyze real data in R rather than just staring at a bunch of equations on my notepad. Today, we're going to be going back to that prescription drug data set that we looked at way back at the beginning of the course, but now we have a lot more tools in our repertoire that we can use to try to analyze it with time series, basically. So let's get into RStudio and see what that's all about. All right, so we're here in RStudio, and our goal is going to be to fit some ARIMA models to the data. So the first thing I'm going to do is load in a bunch of standard time series packages, like the TSA package, the T-series package, and the forecast package. And I will also upload all of this code onto eClass. It should be uploaded like I would my normal lecture notes, so that you can try it yourself, rather than trying to write down everything you see on the video, which would be kind of annoying. Anyway, I also wrote this quick function, which I'm going to load in. I call it plot box test because basically what it does is, well, it plots a bunch of box tests. Remember, we looked at the box Pierce and the Leung box test in R. Both are run with the box.test function. And do you remember what they're for, right? They're for testing whether or not our residuals have any correlations in them. So remember, we estimate the autocovariances, and we try to determine whether or not any of them are significantly different than 0. So all I did here was write a function that runs both the box-Pierce variety and the Leung box test variety of this statistical test, and applies it to the data at various lags, starting from whatever the degrees of freedom are and going up to 16. Remember, we have to tell R how many degrees of freedom we used to fit our model so that we can subtract them before we run the box test. So that's all that this function is doing, but it's going to give us some nice plots a little bit later on when we actually have, models and residuals to look at. Okay, so most importantly, we're going to load in this prescription drug data set. If we go back and look at the manual page for it, we have the cost per prescriptions time series, the monthly US average prescription cost for the month of, it looks like whatever 8 is, which I guess is August of 1986, all the way up to March of 1992. Again, I don't actually know what the units are because I didn't dig into this textbook to find it, and the R package is quite nondescript, but that's okay. We have some unit, presumably per capita or something, spending, and it looks like this. So it's definitely not stationary from the first thing we notice. Secondly, we also notice that not only is it increasing, but it does seem to have some humps here, and that is really hinting strongly that there's some sort of a seasonal model going on. And if we look really closely, we might notice that these bottom peaks seem to happen right around the year mark, which is also hinting that there might be a cycle of length, a period of 12 in our data. But again, these are all things that we're going to try to test and try to sort out when we stare at our this prescription drug data set using different tools. So the first thing I think we should try is to look at both the augmented Dickey-Fuller test and the Philip-Perron test. So ADF test says we have a very small p-value. What does that mean? Well, that means that we reject the null hypothesis that there is a unit root in our, I guess, autoregressive polynomial. That is, we reject non-stationarity and conclude the alternative hypothesis that the data is stationary, but that's after removing the linear trend, right? Remember, the ADF test, because obviously if we stare at this time series, it's not stationary, it is increasing, very, very clearly increasing. But the ADF test, remember, says it removes a constant and a linear trend. So basically it fits a line to the data with a slope and an intercept and removes that and then looks at the process. And what it says is after removing a linear trend, it looks stationary. So before we go forward, let's try the PP test. And that tells us more or less the same thing. It gives us a small p-value. So again, it's not as small as 0.018, but it's still fairly small. So these two tests together make us think that probably our time series is stationary after we kind of tilt it. We get rid of that linear trend just for the sake of exposition, right? The PP test or the Phillips-Perron unit root test is really doing the exact same thing as the augmented Dickey-Fuller test. It uses a different technique, as we discussed in a previous lecture, for estimating and computing test statistics, but the end goal is the same and the interpretation of the p-value is the same. Right. So we have that, and what it told us was if we remove a linear trend, we should have something that looks stationary. So let's just remove a linear trend and see what we get. So what I'm going to do here is fit a linear model to my data, the prescription drugs data, just using the LM function like we would in regression class. And I tell it that I want my response is the time series itself, and the predictor is just the time. And what we get, actually, let me plot the prescription data again so you can actually see what we get. It's always good to look at the models fitted to the data. And if we draw a line for our linear model, color it red, we get a straight line. And it actually looks like it's a pretty good fit, right? I mean, it's kind of hitting all of these humps here in the latter half of our time series. But what we can also do is look at summary to see what it tells us. And it gives us an intercept term. The intercept is kind of nonsensical because it would correspond to year 0. But the time variable is quite interesting. It's very, very strongly significant. And it tells us that the increase is about 2.8 units, dollars per whatever, per year. Remember that the time series here is indexed by year, even though it's sampled every month. So this is a subtlety to remember, that if we look at the prescription, the time for our prescription drugs, we have observations for every month, but the unit is every year. So when we look at a time or a linear model like this, the rate of change is per year, not per month. So it's always good to keep this in mind because it's an easy way to make a mistake and to look silly when you're trying to talk about data if you get the units wrong. But yes, so that's what we have here. And our linear model also, if we use the usual things like the F statistics, right, it has very strong p-values, very big R-squared values. We do have to be a little careful, though, because remember, the linear model is assuming uncorrelated IID errors, whereas in this case, we don't have that. We have, correlated, potentially. Well, I should say we potentially have correlated errors. We don't know if we do yet. We do, but we don't, a priori, we don't know that we have correlations in our errors. The next thing we need to do is look at the residuals and determine whether or not there is some pattern in the residuals. So if I put the residuals into my dat.res thing here and plot it, I get something that looks like that. So if you ever see residuals that look like that, you think, yeah, there seems to be something a little bit peculiar here. Mainly, there seems to be some periodic fluctuations in my residuals. Remember, in regular linear regression, the residuals should look more like white noise. They shouldn't have any discernible patterns like that, or else the model is not a good one to fit. So let's look at, and this is just the 0 line to show that they're kind of about 0. They do dip below. So another thing to note is that they start up above 0, then they kind of dip down, then they start to, spread out a bit, but they are kind of going back above 0. So it also makes me think there could even be a little bit of nonlinearity in here, like a quadratic effect in time. But for now, we still have this intuition from our unit root tests that we should have something that looks stationary once we remove the linear trend. So what it's basically telling us is that this time series here appears to be stationary. So if it's stationary, then let's look at the autocorrelation function. Okay, so if you see an autocorrelation function that looks like that, it's kind of screaming there is some periodicity in my data. There is some kind of repeating pattern. There's probably some seasonal trend going on here. Not necessarily, but that's usually what you see. And I think if we really wanted to, we could take the lag to something like 30. Now the data size itself, I think, is only like 68, 70 data points. So it's not really great to go this far out because you're getting much worse estimates at 30 lag than you would at a lag of 5. But we still do see this nice periodic fluctuation. And we could even take a guess that we see that, it seems to drop down at around 5 or 6 to its lowest point. Then around 10, 11, and 12, it reaches a peak. It drops back down at what appears to be maybe 17, 18, 19, and then comes back around again at 22, 23, 24. So there does seem to be a hint that there might be a cycle of length 12 in the data. And that's natural to think about because it's monthly, right? So whenever you have monthly data, a period of 12 is a really natural seasonal trend to look for in a time series. It doesn't have to be there, and maybe we'll find something else interesting. But I'm just going to delete this so we're back down to the more sensible thing. So that's what we learned from this. And furthermore, the time series doesn't just immediately vanish. So there's probably it's not just a moving average model. It looks kind of like an autoregressive model in the sense that it's fluctuating, but it's also decaying a bit as we go. When we look at the PACF, we see, some different behavior. Now we see a big spike at lag 1, and then everything else is pretty negligible. It's all below the noise floor. Now maybe there's some periodic behavior here, but we don't quite see that. So do you remember what happens when you see a PACF plot that has a big spike at lag 1 and then kind of vanishes right after that? Do a dramatic pause. It's hinting that we have an autoregressive process of order 1, because remember, an autoregressive process of order P will have its PACF vanish as soon as the lag goes beyond P. And here we see a very strong signal from the PACF at lag 1. It immediately vanishes once we get to lag 2, and then all of these are below our noise floor. Now, again, our data size is not massive. In fact, why don't we just look at it so I know what the number is. Yeah, so the data size in this case, yeah, was 68. That's what I thought. So it's not giant. It's not a giant time series. So the noise floor is a bit big, but we still see that it seems to vanish. And that's hinting that there might be an autoregressive process of order 1. And this is a non-seasonal component. So we have two things going on here. It feels like there's an AR1 non-seasonal. And then from the ACF, it feels like there's some type of seasonal, possibly AR process, possibly not going on here. But that's the intuition we can gain from staring at the ACF and the PACF plot. So let's try to fit some models. In this next section, what I have is I have 3 different ARIMA models, non-seasonal at this point, just regular ARIMA models. I should say ARMA models because the differencing is 0. Because I already removed the linear trend, I'm not applying a first difference. Now, a first difference would remove a linear trend, but I already did that using the LM function. So we don't need to do it a second time. Right, so I'm going to fit my 3 models. This is AR1, MA1, and ARMA 11. And now what we can do is we can stare at these. I'm going to give myself a little bit more room down here in the terminal so we can see the output. Right, so our AR1, we get, a pretty strong value of 0.78, kind of like what we see here with this big spike. And that seems reasonable. The standard error is quite low, so that kind of gives me a feeling that this is probably a nice, at the very least, this seems to be a significant coefficient if we consider the idea of asymptotic normality that occurs when you're fitting these models. Okay, the AIC is only for comparison purposes, so we don't know if this is good or not. And the same with things like the root mean squared error. But when we look at the next model, now we have something to compare it to. Okay, so for the MA model, we still see a significant coefficient estimate compared to its standard error, right? If we saw something here like the mean, where the mean right now is much smaller than the standard error, it makes me think that the mean is not statistically significantly different than 0. But the MA coefficient is very different than 0. That's a good thing. But if we look at the AIC, it is now 121, whereas if we go back up, we saw that the AIC here was only 100. So the first model is looking a lot better in both AIC and BIC and this corrected AIC, all of which are about 20 units of information criteria bigger in this second model. And right, we want these things to be as small as possible. So right now, the AR1 is looking much better than the MA1, but maybe we want to include both an AR and an MA piece. In this case, we get a marginally smaller AIC. If we go back up to the AR1, we had a 100.75. Now we have a 100.28. So it's marginally better. The MA coefficient does not look that statistically significant. It is bigger than the standard error. It's not massively large. So there could be something happening there, but it's not clear. The AIC did not change much. So it's kind of like I got a new parameter that improved the fit a bit, but I also lost some points because I included another parameter. In the case of the BIC, it actually, I think, went up. Right, if we go back to our BIC here, it's 107.4. Down here, it's 109.6. So now we have an issue. The AIC went down very slightly. The BIC went up very slightly. I think our adjusted or corrected AIC is a 100.9 for the ARMA. It is a 101.1 for the AR. So it's not clear which model fits better than the other with respect to the information criteria. For the sake of going forward, I just chose the AR1 model because it's simpler. It has fewer parameters in it, and that's the one I thought, well, they're probably going to give about the same fit to the data, so why don't we just take the AR1 and see what that tells us. Actually, it's funny. I'm going to go off script for a second. I'm curious to see what happens if we just try to fit an AR model to this data, if it decides that it wants more than with the Ewell-Walker equation, which is, again, is separate. Remember when we're using the ARIMA function, we're using maximum likelihood, whereas if I type in AR, it defaults to the Ewell-Walker equation, a slightly different way to fit the parameters. For big data sets, there's really no difference. But for small data sets, there will be some differences. Anyway, let's see what happens. Okay, so it gave me a bunch of parameters, actually. It gave me 5. Yeah, that's actually quite interesting. That might be hinting that there's more going on here than just a simple AR1 or even a ARMA 1.1. Maybe there's actually more to look at. But for the sake of the code that I pre-wrote for this lecture, we're going to stick with just the AR1 process for now. We're going to do more models later. This entire lecture is prescription drugs, so get comfortable with this data set because we're going to be looking at it for, well, a while, at least until my voice or tea runs out. Or the code runs out, ideally. Anyway, now that we have these models, I'm going to extract the residuals from the AR1 process so that we can look at them, right? And this is what the residuals now look like. So just in contrast, remember where we started? We started with the prescription data. We fit a linear model to it, which kind of shifts it so that now it doesn't have that linear trend anymore, and we had residuals that look like that. So that's like I said, is no good. That's definitely there's definitely some trend in there. When we plot the residuals after fitting an AR model to the residuals, right? So we have residuals of residuals, right? We fit an AR model to the residuals of our linear model, and the residuals of the AR model look like this. So now they're starting to look maybe a little bit more white noisy, right? That's what we're going for, right? We're trying to get rid of all possible correlations in our residuals. So let's plot the ACF. Okay, so now we don't see any big spikes, but we still see a weird periodic trend. In this case, it oddly enough seems to have a spike at 5 and a spike at 10, and then there's another one at 12. So now it's asking the question, is there actually a cycle of period 12 in a seasonal trend of period 12 in our data, or is it something else like 10 or 5? I don't know. Let's keep going. We'll look at the PACF, and the PACF also seems to have this negative spike here at 5. So that's a bit strange. Well, what we can do is we can try to use the box test to determine whether or not the residuals, whether or not the correlations, the autocorrelations computed for this residual process are significant or not. So I just type in box test and I plug in my data. And if you're reading the comment here, yeah, that's wrong, right? Because what you might do is you might just think, I remember box test tells me whether or not these autocorrelations are significant or not. So I'm just going to take my residuals and shove them into box test. But that would run into some trouble because we forgot to account for the fact that we've actually fit a few parameters to our data. So we had this residual process, and what we did was we fit an AR1 to it. We also had a mean. So if we go back to the summary up here, well, not this summary, the first summary, what we actually fit were 2 parameters. We fit a mean to our data, and we fit an autoregressive order 1 process. So what I had to do instead was actually decrement the number of degrees of freedom by 2, and that means we have to start at a lag of 3 or higher. Remember from that lecture where we introduced the box test, we need to make sure the lag is at least 1 unit greater than the number of parameters that I fit in my model. And if I do that, well, now I get a p-value that looks a little bit more significant. It looks like it's about 1.5%, which is much more interesting than 14%. But if we look again at our plot here, we see this biggest spike around 5. So what would happen if I changed my lag to 5? Because remember, we can run the box test at lots of different lags. If we do that, well, now we get a p-value that's about 0.12% or 0.13%. So now it's looking pretty significant. And similar to the picture of the ACF plot here on the right, what we find is that, yeah, there are still some significant correlations in these residuals. So we're not done yet. We have to try to fit a better, more complicated, a seasonal, in this case, model. But before we're done, we can use that function that I wrote at the top of this R file, which is called plotboxtest. And if I give it the residuals and the number of degrees of freedom to decrement, then what it does is it plots both the box-Pierce p-values and the Jung-box p-values. I still haven't figured out if it's Jung or Leung. I found both pronunciations online, and it was really bugging me. The researcher whose name is Greta Jung or Leung, who apparently is from Finland, or a Finnish American according to her Wikipedia page. And I kept trying to figure out how to pronounce that, and I'm not sure if you're supposed to keep the L silent or not. So sorry, and the very, very, very rare chance that you actually ever watch this video, I apologize for not knowing whether or not the L is silent or not in your name. Anyway, tangent. What I plotted here was the p-values for the lags. I should have changed this index to lags here, but I plotted the p-values against the lags from, in this case, on the log scale. And each of these gray lines is a power of 10. So I have 10%, 1%, 0.1%, 0.01%. And what we see is that, okay, if we do 3 or 4, then we get p-values that are above 1%, but then quickly they drop down to about 1 in 1,000, then they drop down to like 1 in 10,000 as we increase the lag. So this is pretty clear that these p-values are getting very small as the lag increases, and there are some significant correlations in our residuals. So these are all just telling us the same thing over and over again, but I'm just trying to show you different ways that you can look at a time series process, right? You have ACF, you have PACF, you have the box test, you have the 2 different versions of the box statistic, which, yes, are going to give you similar p-values, but you can still compare them, and you can use all of these to get some sort of big picture about what's happening. And at least here, what's happening is that our residuals have some correlations in them. So we're going to do what my comment says here and try some seasonal models. So what I'm going to do is I'm going to keep the AR1 in my data, the non-seasonal AR1, and that's what this first bit says. It says, give me an AR1 process, not seasonal. And for the seasonal model, give me a seasonal AR1. And in this case, I chose a period of 5. I chose a period of 5 because 5 was the biggest and, I guess, spike in my ACF and PACF plots here. Now, granted, yeah, there are spikes that go above on this other side, but I thought, why don't we just try 5? Even though intuitively I really want it to be 12 because 12 months of the year, but let's go with what the data says. Anyway, besides that, everything is the same. I just included a seasonal component. Now, note that I had to tell it a list, give it a list object, and tell it that the order is within the list, and the period is also within the list. So there's 2 components to the seasonal model. It's the order of it, and there's the period. Right, so we can fit that. Then I do the same thing, but I change my AR1 seasonal model to an MA1 seasonal model. And then we do a seasonal ARIMA 1 here. So I'm basically doing the same models as I did before, except I'm doing them seasonally rather than just looking at them non-seasonally. Well, now that we have these 3 models fit to our data, we can just look at the summary and see what we get. So remember, these models also are applied to the same residuals from our linear model, so we can compare the AIC and BIC values to those that we found before. And if you recall, the new ones are here, so you can kind of see where we're going with this. But if we go back to our original non-seasonal model, what we had was an AIC close to 100 and a BIC of about 107. So what happens when we add in a seasonal AR? Well, wow, the AIC drops now to about 89 and the BIC drops to about 97. So this model is fitting a lot better to the data than the previous one without the seasonal component. Note that now we have 3 parameters being fit. We have the AR1, again, a pretty big value compared to its standard error. We have the seasonal AR1, in this case it's negative, which kind of makes sense because we saw a negative spike here in the other residuals. And then we have our mean, which is still looks pretty insignificant, but that's okay. We don't really care about that. I mean, we already removed a linear trend, including a slope and an intercept, so it kind of makes sense that the mean should be not interesting, but it's included here anyway. I think you can force the ARIMA function to not fit a mean, but we'll just leave it in. It doesn't really matter. Anyway, so we have that, but then we still want to know how our other models do. So if we replace this seasonal AR1 with a seasonal MA1, well, now the AIC has increased a bit. Here we're about 89, here we're like 94, 95. And similar with the BIC and this corrected AIC, they all increase. So it's telling me that, okay, this is still a model that seems to fit the data better, at least with respect to information criteria, than what we saw for the non-seasonal model above. But it's still not doing as well as our seasonal AR model. And then lastly, let's look at the seasonal. Wow, what did I just do? I think I just ran everything. Well, that's, I guess, spoiler alert. Sorry about that. I didn't even know you could do that in R. I'm not sure what button command I hit that just ran my entire code, but let's just go back up because I think I just overwrote some of the functions. So, even when I carefully write out all the R code beforehand, things can still go awry. Okay, so now I've refit all of these and we're back to where we were before. And if we look at the seasonal ARIMA 1.1 model, well, now we get an AIC that has dropped a little bit. It went from, I think, 89 to just a little bit below. Basically, it dropped by about 1 unit. Now it's 87.9. And our BIC is 99, whereas our previous BIC was 97. So once again, we're faced with a dilemma. The BIC went up slightly. The AIC went down slightly. What model should we pick? Well, honestly, they're probably going to be doing about the same thing. I think here the root mean squared error for the training set, that is the data set, the error tested on the training set of the data set itself. You can give it a training test set if you really want to, but in this case, it's just doing the root mean squared error on its own data. We get a 0.42. If we go back up to that other one, well, we got a 0.43. So it's slightly worse, but not by much. Again, there's a bit of an art to this, and it's not really always straightforward what the right model is to pick. So in this case, I'm going to just decide that we'll stick with the seasonal ARIMA 1.1 model, and we'll go forward with that and see what we get. So, now we have a model that has a non-seasonal AR1 and a seasonal ARIMA 1.1, and then there's that mean, which again, we don't really care about. All right, so let's look at the residuals for this model. Oh, I have it. Oh, I think I chose the other one. Well, let's choose this one. Let's look at the residuals for this model and see what we get. All right, so these are the new residuals for our model. If we look at the ACF, what do we get? Now everything looks like it's below the noise floor. I like the looks of that. PACF, everything's below the noise floor. Okay, so that's 2 for 2 right now, where we don't see anything interesting happening in either the ACF or the PACF. Let's use my plot the box test function. And what do we see? We see tons of p-values. Note that I had to change, I changed this to 3, but actually I should change this to 4 because I fit a non-seasonal AR1, an ARMA 1-1 seasonal, and a mean, so that's 4. Okay, so if I do that, the first 4 p-values are set to 1 because they don't count. We need to look at lags of 5 or greater, and in both cases of our 2 different test statistics, all of our p-values are at worst around maybe 10% or 20%. Basically, there's nothing significant here, which makes us think that our residuals, which again look like this, are uncorrelated, and we actually are in a good state. Hooray. So now what we can do is we can actually do some forecasting because we have a model that has accounted for all of the correlations in our residuals. And that's really the goal here, right? The goal is to try to identify all of the time series pieces, the AR, the MA, the seasonal bits. And then when we remove those and we're left with just the residuals of that thing, it should just look like white noise. And in this case, that's what we got. We got something that looks like white noise. Oops. And that's good because that means we can then try to do some forecasting. So I'm going to go back to my 1-1, and this is what we get for forecasting. And remember, we're forecasting the residuals of our linear model. So remember at the beginning, we fit a line to the prescription drugs data, and then we looked at the residuals, and we're trying to fit time series to the residuals. And what we get is something that looks like this. So what is this telling us? Well, it seems to be pretty clearly capturing the periodic nature that we see from the actual data here in black. And it's also decaying as we go off into, I guess, the future, as we predict further and further into the future. Here I predicted 50 time points. If we were to predict 500, I always do that, 500, it eventually kind of decays back to 0. This is because of that AR1 piece, kind of pushing it. Yeah. I guess it's also the other piece too. Yeah, the AR, I mean, both pieces would kind of decay as you go off into infinity, right? So that's where we see this going. We see it just sort of decaying off to the mean, but at the very least, we get a sense of what it's doing in the near term. So if we don't go out to like some stupid number like 500, if we just look at the next 50 months, so this is like saying we look at the next 2 years of prescription drug prices, we expect to see some periodic fluctuations in the residuals, but ultimately there's that linear trend that says drug prices going up by about $2.8, I guess, whatever unit of dollars per year. With residuals that will be fluctuating in a sort of roughly periodic pattern like this. Now, if we were to ignore the seasonal part, what would it look like? Well, I can still take my AR1 non-seasonal model that I fit further up on the page, and I could try to forecast with just that. And in that case, yeah, it looks a little bit weird, right? Oh, you know what? I completely messed that up. It's because I accidentally ran all my code and I overwrote it. So I don't want that plot yet. What I want to do is refit my non-seasonal models. The problem with this code is that I overwrite the models in the next section. So what that means is that this is not the model that I wanted to fit. So we'll do a quick little correction there and figure out where I was in there's my forecast. So going back to where we were, this was the forecast with the seasonal component in it. If we try to forecast the residuals without a seasonal component, we get something that looks like that. So it just basically says, I'm just going to go right back to the mean, sort of regression to the mean in a sense. Not exactly the same concept, but the same idea that we're just going to, our time series is going to go right back to the mean after about, I don't know, let's say 68 to 80. So I guess 1 year from now, 12 months from now, we're basically back, the residuals are back to the mean, and we don't really know where else we're going. If we look at this data, then we still see periodic fluctuations that seem to happen about every maybe 5 or 6 units for these spikes. Again, we had a period of 5, and it does seem to fit the data really well according to all of the test statistics, the ACF, the PACF, the box test that we have. The other thing we could do is we could look at things like the forecast error. So when I refit, well, I didn't do the summary, but we could look at things like the root mean squared error, the AIC. These all give us different indications of how well they fit, how well these models fit the data. But we have another tool in our repertoire, and that is, oh wait, we haven't gotten there yet. There's one other thing that I wanted to do, yes, before we try ARIMA models, and that is, let's just try to force 12 months in there, because I really want it to be like a 12-month period, not a 5 or a 10-month period. So let's see what happens if we try to do this. Again, overwriting the previous model. Let's see if we overwrite it and try to do 12 months. And what do we get? Well, we get an AIC that's still better than the non-seasonal model. It's not as small as the one of order 5. In this case, order 12 is giving me an AIC of 93. The order 5 was like an 89. So it is, the order 5 was giving us a smaller AIC in this case. But we can still look at the residuals. And what do we see? Well, those are the residuals for the process fit with the seasonal period of 12. It still looks pretty noisy, but as I've often said in this course, it's hard to tell what's going on with residual plots. It's better to use things like ACF. In this case, we still don't see spikes going that far above the noise floor. We do see a spike at 5. Because the data size is not massive, it's debatable whether or not these spikes at 5 and 10 are actually significant or not. The PACF, we also don't see anything going above the noise floor. When we use the box tests and the Young box test, what we find is that, yeah, we do have a few p-values that drop below about 5%. They don't get down to 1%. So again, it's kind of ambiguous. I get the sense that this model with a seasonal period of 12 is not doing as good of a fit as the one with a seasonal period of 5. So for whatever reason, the one with 5 did seem to fit the data better than the one with 12, at least fit the residuals after removing the linear trend, as we did at the beginning of this R code. Right, and then we can also do forecasting just to see what happens, and we get something that looks kind of the same. Again, it fluctuates up and down a bit, taking into account the seasonal trend that we fit in this model, but eventually it kind of regresses right back down to the mean in the, I guess, English word of regress and not in the statistical word of regress. It tends to the mean as we predict further and further into the future. All right, but instead of using linear regression to remove that linear trend, we could just use the ARIMA function itself, because the ARIMA function allows us to do a differencing. And as I've mentioned, when we have a polynomial trend in our data, if we take enough differences, first, second, third differences, we'll remove that trend. So if we have a linear trend in our data, we might actually want to fit an ARIMA model with a first difference to get rid of that linear trend. So let's try it. Well, first, let's just look at the first difference. So if I take the first difference, it's not going to be, it's different, right? It's different than the residuals above. For the first, this is kind of like part 2 of the lecture. In part 1, just to emphasize what we were doing, was that we fit a linear model using the LM function, and we tried to fit time series to that process. Those are the residuals of the linear model. Now, what we're going to do is we're going to look at the first difference process, which is a different time series process. So a different time series model may actually work here. As usual, I'd recommend that we start with the ACF and the PACF because, again, based on the very beginning when we did both the Dickey-Fuller and the Philip-Perron test, we saw that after removing a linear trend, this thing looked stationary. Therefore, doing a first difference would also mean that this would look stationary. So it's reasonable to do ACF and PACF. If we don't have a stationary process, we can't use these because we'll get weird, erroneous results. Okay, so what in the world is this? Well, a couple things happened. First of all, now it's doing fractions of a year on the horizontal axis. And if we count 1, 2, 3, 4, 5, we still see a spike at 5 for whatever reason. So that's actually still there. And then 6, 7, 8, 9, 10 spike, 11, 12 spike. So this is kind of strange. We seem to have a spike at 5, and we also have a spike at 10 and 12 for the ACF. For the PACF, we don't see it as clear-cut as before. Remember before, we saw that big spike that indicated that we have an autoregressive process of order 1, whereas now it looks more possibly periodic, but most of this is happening below the noise floor. We still see a spike that's at 1, 2, 3, 4, 5. So again, 5 seems to be the magic number here for some reason. We can always try to just fit an autoregressive process to our data just to see what happens using the Ewell-Walker equations. And note that I'm fitting it to the first difference of the prescription data. And we get an order 7. Okay, so that's indicating a couple things. It's indicating that we probably don't have a pure AR order 7 process. We probably have either a moving average piece or a seasonal autoregressive or a seasonal moving average piece or some combination of those. Interesting though, we note that the first coefficient and the second coefficient are really small. The third one is relatively bigger, then small, then 5 is bigger, 6 is bigger, and 7 is starting to get a little bit smaller again. So again, the biggest coefficient here is actually order 5, and again makes me think maybe there's some order 5 periodicity to our data. It's negative, so it would kind of be like go down at 5, go up at 10, go down at 5, go up at 10, if that makes sense. Anyway, it never hurts to like fit a bunch of models and just see what they do. So I'm going to fit a couple models. The first one is just a first difference. And if I just take a first difference, I'm basically looking for white noise in the process. Now, because of these spikes here, I'm guessing that that's actually, no, it's funny. I never actually did my box test. We should do the box test, my plot box test function, where if I give it the first difference and my prescription, now in this case, we haven't actually fit any parameters to the data. We just took a first difference, so I can set this to 0. Hopefully my code handles that. It does. Excellent. And we actually see very significant lag or significant p-values for small lags. They eventually kind of go away, but that again is indicating that, yeah, we probably don't have a stationary or we probably don't have uncorrelated residuals here. Now, I can fit a model that just assumes that we have a random walk. This is basically like the random walk or the linear trend model. It's saying that if I take a first difference, I want to get white noise, right? Usually we want the residuals of these to look like white noise. So if the first model is true, then it's basically saying I take a difference, I get white noise. In this case, we have the AR1 with a first difference, the MA1 with a first difference, and the ARMA11 again with a first difference. So let's stare at these and look at AICs. Now, the AICs here are not comparable to the ones we did before because these are for a different time series. So remember that we're doing something a little different here. Well, this one, as a baseline, gave me an AIC of 114.3. Okay. If I look at the AR1, well, now I'm at 110. That looks better. If I do the MA, I get a 112. That's a little bit worse. If I do the ARMA 11, I'm at 110. So I think that was really similar to the previous one. The BIC is 117. If I go back up here, I get a 115 and a 110. So right now it looks like the model 0 or 10 being the AR1 model with a first difference, remember, is the best one with respect to AIC and BIC. So let's look at the residuals, right? This is exploratory time series data here. We're just kind of fitting models, looking at the residuals, doing it again and again to try to understand what's going on here. And we can look at the ACF. Actually, I didn't plot the residuals. I always like to plot the residuals because it's always good to look at the data. Rule number 1 of statistics, look at the data. And that's our residual process. Is there something periodic going on there? I don't really know. So we'll look at the ACF and the PACF. And once again, we do still see some spikes above and below here in the ACF and the PACF. If I try to fit my plot box test, in this case, I can give it my ARIMA res. In this case, I fit only one parameter. Oh, it's not here, it's down here. I only fit one parameter because when you take a first difference, by default, you're not fitting a mean because the mean would be first differenced into oblivion anyway. So by default, it says, well, I'm not going to fit a mean because you just took a first difference and you would have deleted the mean anyway, so there's no point. We can fit a drift, though, and that would be something interesting to consider later. But right now, we're just going to say that we have one parameter. And yeah, in this case, we see it's kind of going in the opposite direction. We start off with insignificant test statistics, but as the lag increases, suddenly we start to get more significant test statistics at the 1% and at the 0.1% level. So that tells me that, we're not done yet. We probably need some type of a seasonal model, especially based on those ACF and PACF plots. I just did another lecture before this, so let's keep that voice going for just a little bit longer. All right. Let's try to fit some seasonal models. Well, we can fit the seasonal AR1, the seasonal MA1, the seasonal ARMA11, and then we can stare at the summaries. So in this case, we get our AIC of 110. Okay, that's kind of like where we were before. Now we get an AIC of 111. That's worse. Ooh, an AIC of 106. So in this case, having a non-seasonal AR1 and a seasonal ARMA has actually given us a smaller AIC. So that seems like it's giving us a good AIC. Let's try and forecast and see what happens. So if you notice my green comment here, does this look like a good forecast to you? I mean, right, if you fit this model and you took it to your boss at the pharmaceutical company you're working for and you said, this is where I think drug prices are going to go, you're probably going to get fired because, it should be going up, right? It's probably not going to just start going horizontally. So something went wrong here. Now, let's look at the residuals of this model. And we can plot the residuals. That looks pretty noisy. We can plot the ACF. That looks like it's below the noise floor. We can plot the PACF. That has, well, it still has a spike around 1 year. So that's kind of hinting like there might be some order 12 thing going on. And I can plot my my test statistics here for the box test. I do get a few p-values that are dropping around the 5% level, so nothing like strongly significant, like 1 in 1,000, but we still have some p-values that are looking a bit significant. And remember, I had to take away the 3 parameters that I fit, being the non-seasonal AR and the seasonal ARIMA 1-1. Okay, so, maybe this model is not a good fit to the data, but it's a little confusing, right? It's like, I wonder what we could try. We could try other periods. We could try to put in a period of 12. Or you know what? Maybe we should just use auto ARIMA, because auto ARIMA is going to just do it all for us. And then we type in auto ARIMA, and what does auto ARIMA come up with? It comes up with a first difference. So there's no non-seasonal part here. We're just taking a non-seasonal first difference, but there's no AR, there's no MA. And for the seasonal part, we just have a single AR1 parameter and a period of 12. So there's the 12 that I was kind of hoping would show up here. And not only that, our AIC is now 79.9, which is lower than that 80 whatever that we had with our previous. No, I think our previous model was like 100 or something. Yeah, it's like 106. So we're doing a lot better AIC and BIC wise. Notice that the mean squared error and some of these things don't actually change that much, but, well, actually this one changed, I think. Yeah, the absolute error dropped a bunch, but the mean squared error not as much. Okay, so maybe we want this model instead. Let's take a closer look at it. All right, so we have our new model. It was fitted by the auto ARIMA. And remember, auto ARIMA is going to try a lot of different seasonal and non-seasonal ARIMA models and choose the best one with respect to AIC and BIC. Now, you do have to be a little careful, because sometimes you might get a slightly more complicated model than necessary because the AIC is marginally smaller than another equivalent model. So sometimes it is good to try other ones. Now, this one looks pretty simple. There is no non-seasonal piece, and there's only a seasonal AR1. So I kind of like that, because I love my simple models, kind of the Occam's razor approach. It's the simplest model is often nice to see. Now, just to take note, you can tell it what order to check for the AR, for the MA, for the seasonal AR, for the seasonal MA, and all of these pieces, and also where to start and things like that. You do have to be a little bit careful, because this function can be computationally taxing if you have a really big time series and you want to search a lot of parameters, to the point that you can actually parallelize it. And I think by default, no, it doesn't parallelize by default, but you can parallelize it on your computer to speed up the running. But what you really want to do is see what the forecast looks like. So now that looks like a good forecast, right? It's kind of heading off in the direction we want. It looks like it naturally extends from our data and continues to increase as we move into the latter half of the 90s or the mid 90s. And we still see this fluctuation here up and down from our seasonal component. If we were to increase this really far into the future, we see that the variance really spreads out here, right? This is the one problem with our first difference, in the sense that the variance is going to keep increasing, and when we're out in 2030, we have no idea what prescription drug prices would cost. Hey, maybe they're going to be negative. That's probably not the case, but oil went negative when COVID hit, so hey, you never know what could happen. That's probably not going to happen. They're just going to keep going up. But the point is that you can kind of see the long range behavior of our prediction, though typically we wouldn't be predicting that far into the future. We just want to predict the next year, the next couple years, and it looks pretty reasonable with what we get. Now, what else can we do? Well, we can look at the residuals. Again, it's always good to look at the residuals for this model to make sure that it actually is good. There's our residuals. Yeah, this is a little bit funny, the way how it just fits the beginning really, really well with that. And then we have some noise. ACF looks really good. PACF looks really good. Box tests. What in the world did I do again? I hit it again. It must be when you hit Shift, Control, Shift, Enter, I think just runs all your code at once. Anyway, this is what I wanted to show you. Luckily, we're almost at the end, so I didn't overwrite too much, but yeah, all of our box test statistics seem to have insignificant p-values. That's a pretty good hint that this model, the one chosen by ARIMA, is actually a really good one. Though, I would encourage you not to just use ARIMA and take whatever it gives you. Try some different models, see what they do, and explore the data, and don't just pick the first one that this one spits out at you, because there are other things you can try with the modeling, and it is really good to explore your data and not just take whatever the code gives you. Even though in this case it gave us a really good model. So thank you, auto.arima, and whoever coded it. Let's check. Who coded this? It must have been, usually there's authors on some of these. Rob Hindman, or Hindman, we'll say. Well, thank you, Rob, for coding this. It worked really well on this data set, so I'm glad that we have access to it. But before we're done, let's just fit some other models, because we kept seeing that weird period of 5 showing up. What would happen if we tried to fit the same model, which is an AR1 with a period of 5 and no non-seasonal piece? In this case, well, the AIC is a lot bigger. It's no longer whatever it was, 79.9. It's now well up over 110, 114. And what happens if we try to forecast with that? Well, yeah, that one just kind of dies off. So that's no good. But we could try an AR1 and non-seasonal and seasonal. And what would that do? So if we try to include an AR, I did it again. It's a problem hitting these buttons with my fingers. So if we try to include an AR1 piece, the AIC actually jumps up from 80 to close to 100. So that's actually doing much worse. And if we were to plot that forecast, we see that it kind of increases and then it just kind of dies off. So it's kind of a funny looking model. If you look at it in the long range, what it does is it keeps increasing for another year or two, and then it just flattens off because of the way the AR1 piece, the non-seasonal AR1, is influencing the seasonal bit. In the long run, it's just pushing it to like shut down and go to the mean. Okay, we have one more model to look at, and then we're going to be done with this data set. And that's fitting an ARIMA model with drift. So what I could do is, instead of fitting a model with a first difference, remember, I could instead ignore the first difference, but tell the ARIMA function that I want a drift term, because the drift term is going to give us kind of a linear increase or decrease. So here I'm fitting an AR1, and yeah, I'm running off the page. I'm also fitting an AR1 and a seasonal AR1 with period 5, and I'm giving it a drift term. So what does that do? Well, that is going to give me a smaller AIC now. It's not 80, it's 90, but it's still something. It's giving me a drift term, which tells me how much I'm increasing every time step. And I also get an intercept in there, and I get my AR1 and my seasonal AR1. There's no first difference in this case, so it also includes a mean. If I look at the forecast for that, now that looks more reasonable. It doesn't maintain the periodicity. Again, this AR1 piece kind of kills off our periodicity, but we do still keep increasing. In this model, the variance doesn't blow up, which is another interesting peculiarity. So we can look at this more in the equations. But in this case, because we're not doing that first difference, the variance tends to the mean squared error and just stays there. So basically, these lines are this band is corresponding to approximately what we think the residuals, the variance of the white noise process should be. Yeah, and we can look at the residuals there if we really want to. And what do we get? We get that thing. We get AIC or ACF. PACF looks good. And these test statistics look good. So a lot of these models were not good. But this one with a period of 5 and a drift term, WD for with drift, is actually a good fitting model. It does have a higher AIC than the one auto ARIMA chose, but we're still getting very strong statistical results. Lastly, let's look at that linear model again. So this told me that I should have an increase of about 2.8 per year. Well, a year has 12 months, so that means I should increase at about 0.2345 every month. And up here, the drift term, 0.2370. So here you can kind of see what's going on. The drift term is very similar to the linear model term that I fit originally, but in this latter case, all of the parameters are being fit together, I believe using a maximum likelihood approach, but I would have to double check the documentation. Whereas in the original part of this lecture, we fit a linear model using least squares and then went on to consider the residuals. But the key thing is that we actually get a very similar increase both in the linear model and in our drift model here. Yeah, we're basically done, but just for fun, I'm going to go back up here, and what would happen if we just killed off the non-seasonal part? In this case, I get an AIC that, whoa, that AIC is terrible. Okay, so that's no good. That's actually quite interesting that it's so bad. I guess it completely screwed up this beginning here. So it seems to be like there's something quite wrong there. When I removed the, all right, we'll just forget about that model. It's not interesting. This one seems to be good. If we increased it to order 12 though, yeah, now we're getting an AIC of 95. That's no good. But if I remove that, nope, that still gives me terrible AIC. I was hoping that the order 12 would kind of capture the periodicity in the data, but that is not the case. So I'm going to go back to my original model so that when I upload this, you can see the code that I ran the first time. Yeah, that looks better. It's kind of connecting a little bit better there. All right. So that is exploratory data analysis using for ARIMA models and seasonal ARIMA models in R. There is a lot of fun you can do because it really just comes down to fitting some models, looking at AICs, looking at ACFs, looking at PACFs, doing box tests, doing ADF tests and the PP tests and all these other tests, looking at linear models, adding in drift terms. There's so many different things you can try in order to try to model your data. So hopefully this lecture gave you an idea of how you can approach a time series process if you're trying to analyze it yourself, because there's really no right answer, right? I mean, we can find different models that fit the data really well. And we can find other models that seem to give good residuals, but then give really strange forecasts. So you have to be really careful when you're fitting time series models to your data. But we'll be going forward into a new section after this. It's going to be on spectral methods. It's a whole sort of right turn into the frequency domain. Maybe left turn is the right way to say it. I forget. Regardless, it's going to be a new chapter. We'll be starting that in the next lecture. So it's always a good day when we get to use... Oh, the Blue Jay is back. I hope you enjoyed this, and I will see you in the next one.